can start recording now. So I'm not sure where this goes later, but yeah, I'll figure that out and upload it somewhere. Yeah.
So maybe another question related to the online proctoring. If I have a scanner in the room and would prefer to use that over like a cell phone, do I just need to angle my computer so it's visible? So when I go to upload it, or how do you want it?
Whatever. I don't think you have to. Like basically I'm expecting at the end everyone is gonna do something that is going to like flag the system or whatever.
Mm-hmm.
Yeah.
Okay.
That's kind of what I'm just assuming right now. Yeah. So yeah, that's whatever you, yeah, if you want to point it at that, that's fine. If not, if it's too difficult, don't worry about it. All right, what other questions are there? All right, well, I'm just about finished writing the exam. So the exam is going to cover chapter 4.3 through 4.5. So in the book, that's basically the amplitude modulation. So basically this is going to be homework written assignment 3. So basically everything, all the type of stuff that was in written assignment 3, that's the kind of stuff that's going to be on the exam. So everything has been a little unusual the last several weeks, including this, but basically I think that includes, if you're going back, lectures from like February 18th and a couple others in before the break, and then all of the lectures that were uploaded, all the video lectures that are up right now. So basically, yeah, all of written assignment 3. And that, yeah, and so if you want to go back and look at some of the old videos, I was checking the other day, and I believe February 18th is like the video where we talked about amplitude modulation in class, and so you could look at that video if you wanted to go all the way back to there. So in the textbook, yeah, it's page 198 to 224.
We're also going to have phase modulation and frequency modulation, right? Is that in chapter 5 or is it just my book? That's weird.
That isn't in the 4th edition. Those are in chapter 5. Yeah, I believe. Although I don't have the 4th edition, so I can't say for sure. Yeah. But you may have checked, but you can definitely access the 5th edition for free via Oxford University Press. So yeah, just the online version. Okay. So
is the exam open book, open notes kind of a thing, or just single page? Does it matter?
I want you to do anything except for like talk to other people or like, you know, call other people or use the internet. But yeah, if you have like other written notes or the textbook or other textbooks, like that's all stuff that I would consider to be okay. Yeah. So yeah, write as many notes as you feel like, you know, write ahead of time. If you have the homework, you know, get that ready. Anything like that. So yeah. And then the format will be similar to the other exam. About the same number of questions, maybe one or two more. But at least a couple of the questions are going to be more like explaining a concept or something. So some of the things that we've talked about are, you know, in some harder to do mathematically, but we have like discussed the concept. So there'll be at least one question that asks you to like, review a concept or describe why you might implement certain types of modulation. So, yeah.
Should we have like the trig identities and stuff, or will you provide that on the exam?
Let's see here. If you need trig identities, I'll put them on, get them ready for you, put them on the exam. Yeah. Yeah. Let's see. What else? Yeah, besides that, it will be very, similar to the quiz where I'll have it set up to start so that you can, click go or whatever at 9:30. And then I'll have it end. I know since there's a little bit of confusion today, I'll give you like 10 extra minutes afterwards just to make sure you have plenty of time to upload, but plan for it to be, similar to the other exam. So sort of mentally plan to end at 10:45, but you'll have 10 minutes after that to get all the scanning and stuff done. And then, everything else should be basically just like this quiz where you'll click on it and click on the start, and it'll take you to the link where you can look at the exam. So
I have a question about amplitude modulation.
okay.
So you know how when you modulate it with the cosine frequency and then you end up getting the sine wave according to like the envelope of the signal?
Yeah.
What's the best relationship to determine how that envelope changes in respect to the mu value?
Let's see. Okay. So more or less like yeah, so if mu is between 0 and 1, that means that your message is going to have shifted such that the lowest values of the message all become positive. So when it's between 0 and 1, when the mu value, the index of modulation is between 0 and 1, that guarantees that the distortionless transmission because the message has shifted. And I'll like make a little whiteboard here. Okay. So, right, the relationship for this mu is MP over A. And so it's distortionless when this is between, and just please forgive how bad this looks. It's hard to draw this with a mouse pad. So when mu is between 0 and 1, this means that A is a large value, larger than MP. And if A is larger than MP, right, that's going to indicate that we were able to shift. So in the book, like if the message looks like this, going from MP to minus MP, if A is bigger than mu, that means we were able to shift it up higher. So that, I guess you can think of this relationship. The reason that if mu is closer to 0, that means that A has become a very large number compared to mu. And that means that we've shifted this up very high. So like if we shifted all the way up to here, right? The higher we shift this, let's see, so this is, come on, go away. So the higher we shift it, the more, actually this is not A. Yeah, the higher we shift it, the lower mu gets. So that's the relationship between them. You can think though of some cases where, right, we might have like, so this guarantees, so I guess backing up, when we have this A so that it's larger than MP, that guarantees it to be distortionless because that guarantees that we've shifted this so that it's all above y equals 0. So that guarantees the distortionless case. However, right, that we could imagine some things, especially when we were looking at some of those digital modulations, we could imagine some cases where there's distortion, but the message is still comprehensible to the receiver, right? And that's because we could imagine, right, like say the original message went from, you know, something, if this is -1 to 1, and we did some shift, but it wasn't high enough. So let's say that it goes, so this is -0.5 to 1.5. So we shifted it some, but not everything. We could see then that if we were to modulate this, we'd have this envelope that goes down to here. All right, now this does not contain the exact shape of the original envelope. Right, the original envelope went from -1 to 1, whereas this one goes from 0.5 to 1. But we still, if we had a very sensitive receiver, right, we still might be able to detect the difference between these two pulses, but it's just not guaranteed to be distortionless, right? So if you're receiving a digital message like this one, you have to be able to distinguish between the -1 and the +1. This one has some distortion, and the distortion amount, right, actually we can even calculate this. In this case, A was 0.5, so mu is equal to 1 over 0.5. So it equals 2. So in this case, it is distorted, but you know, maybe a sensitive receiver could still tell the difference between a 0.5 and a 1.5 in the pulse, especially if you're expecting like a digital message. If this was an analog message, you know, you might be a lot more out of luck here. But for a digital message, you could still put this through something that receives an envelope detector. You could still get the envelope right, the envelope is still going to look like this, which is basically the shape of the original message. but it has been distorted because the pulse is much weaker than it was in the original message. So that's we won't really get into this, too much, but that's one reason why, one advantage sometimes of digital communications is with the digital communication system, right? You have a set number of values that you're already expecting to be receiving, right? Like when you're a receiver, you're saying, okay, I'm expecting the reception message to look like something. Whereas and so we can maybe, do some extra things to decipher it. Whereas an analog message, more like these ones, you don't know what exactly you're expecting it to look like. So distortion could damage that message more. All right. So I think your original question was there some rule of thumb or something we know about index of modulation? And I'm not sure if this answered your question, but hopefully that helps.
That makes more sense. I was just, because we graphed it in MATLAB and it kind of did it for us. So I was just trying to think about how if we needed to sketch it.
Yeah.
And that helped. So
yeah, for a digital message, it's pretty easy to sketch. So just like this one, it's not too bad. But for something like a sine wave, that would be a lot harder to sketch. Yeah, sorry, was there another question?
I had one. So we kind of walked through the mathematical benefits of doing phase modulation versus frequency modulation. Is there like a real life advantage, disadvantage we should be aware of here?
Yeah, so that's like what we're going to get to in the next chapter. But basically, you don't need to get into it too much now, but basically the goal, what they imagined early radio engineers, what they imagined they would be able to do with angle modulation is they imagined they would be able to reduce the bandwidth to 0. However, what we're going to see is that theoretically, you actually end up with an infinite bandwidth when you do angle modulation. It's just that the further away you are from the frequency that you're transmitting at, the power goes way, way down. So we'll talk about that later. For now, for now, all we really know is that is the basic introduction to how those two work: phase modulation and frequency modulation. Yeah. So yeah, does that answer your question at least a little bit?
Yeah, I keep forgetting my mic is muted.
Oh, okay, sorry. All right. What other questions can I answer?
for the frequency modulation and phase modulation,
Mm-hmm.
So on the quiz and test, when we did the cosine part of that, is the length or like phase that those cosine waves are apart, right? Because it speeds up when the slope is higher. Is that how that is determined?
Let's see. I'm a little confused exactly what you're asking. With the so cosine, basically you're asking about the modulation.
Yeah.
Okay, of phase or frequency. You have the cosine of some angle?
Yeah, so so for the sawtooth,
Okay.
and then you modulate that to get the frequency modulation.
Mm-hmm.
And then you're like you're like graphing that, right?
Okay. Yeah, so the message is the sawtooth in your module. Okay, yeah.
How do you changing the I guess cosine wave based upon the slope of the function or the amplitude?
Okay, yeah, it depends on which way you're modulating it, right? So, yeah, so if we want to do phase modulation, right, we're going to directly modulate that angle, the angle of the cosine wave with the message. So if the message is steep, then you're going to get bigger changes in phase. So that's why, right, like if we have a phase modulated message and there are discontinuities, that's why there's going to be those big shifts in phase, because those discontinuities are resulting in instantaneous phase changes. But for frequency modulation, it's a little bit different because you're directly modulating the instantaneous frequency with the message. But in neither case are you modulating the angle. I mean the amplitude. I'm sorry. For both of them, the amplitude is the same, or not the same, but it's whatever you want to transmit it at. You can transmit it at any amplitude. So a cosine of theta in that. So if your modulation, this, right? So if you have some modulation like this, this is the between frequency modulation and phase modulation. You're changing theta, but this isn't doing any of the modulating. This would just be a constant. Yeah. Does that answer your question?
Yeah. And then when you do phase modulation and you're taking the derivative of the function at like the continuous points, right? Because you're only, or is it the discontinuous points?
So yeah, for phase modulation, you would take the derivative to find the instantaneous frequency. Right, so the instantaneous frequency is the frequency of this cosine message at any given instant. So if you have a message, a PM, a message like this one, okay, we can see, right, this is our message, MT. We can see that this message has big discontinuities, right? It's jumping from, say, 1 to -1. And the instantaneous frequency of this, the W omega I, right, this is d theta dt. And theta, right, this is the angle. And we have some carrier frequency, right, that the modulating the carrier is at. So the carrier has some frequency and some be multiplied by some time, and then the modulation we're doing is some constant multiplied by the message. Okay, so we can see, right, that if we take the derivative of this and this part, so if we're taking the derivative of the angle and the message has these discontinuities in it, we can see that the instantaneous frequency, so that's the frequency that this cosine wave is oscillating at, is going to have big jumps, because from here to here, right, there's a discontinuity in the message, and so that discontinuity results in instantaneous frequencies that change in zero amount of time, that change a big amount in a zero amount of time.
How do you know the height and the direction of those impulses that come from the derivative?
Just from looking, I mean, like qualitatively, from looking at the message, you can see that in this case, right, it's changing from a high to a low by amount of 2, and from here it's changing from a low to a high by amount of 2. Yeah. Yeah.
So you would have like a pulse of 2 at a height of 2 going up, and then the next one would be a pulse of 2 going down, right?
From here, yeah. This is like a instantaneous change from 1 to -1. So in zero amount of time. So, and you can still get this to work. Also in real life, one thing that you could just think of, in real life, you can't really make a perfect pulse like this anyways. So, so if you're trying to avoid this, in real life, you could just, I mean, there's things you could do, but to avoid that discontinuity, right, you could make something that looks more like this. And for a digital message, right, like we were kind of talking before, we know there's only, like, if in the most basic case, there's only 2 things to look for, a 1 or a 0, a positive 1 or a negative 1. So that's definitely like one of the reasons why digital communications has some big advantages over analog, is that there's more like a finite number of possibilities that you're looking for at the output, at the receiver end. Yeah. I don't know, did that give more confusion, or was it helpful?
Very good. That was helpful.
All right. Does anyone else have any questions?
Maybe I missed it, but do we have any like equation sheets we can bring ourselves, or is that all going to be provided?
Oh yeah, bring whatever you want. You should bring for yourself. I did say that I would, if there was any like specific trig identities or something like that, I would put them in. But basically, if you can bring your textbook, you can bring as many handwritten notes as you want. You can have the homework there. Any resource you want. The only things I don't want you doing are using the internet, or like calling other people, or like working with someone else. Yeah. So if there's some other equations that you want, yeah, go ahead and write those up, or if you happen to have a printer, print those out. Or it sounds like too, I don't know if you want, but I did find out, if any of you are like worried about your internet connection or whatever, you can use, there's a bunch of the IT labs that are still open on campus. So if you want to just print stuff out in advance or whatever, some of those are still available.
Okay, I was looking at the Examity thing when I was scheduling for it, and it said that there was no other materials that you could bring.
Oh yeah, I think I need to finish updating that. So
I think on your actual part though, when you go register and like agree to all the things, it does say you can have open note, open book, I think.
okay, I
Because
know.
it like starts you and it says, do you agree to this, this, and this? And then I think it said it.
This is for the exam. It was like that on the quiz.
Yeah. Okay. Yeah, I still need to finish writing all that stuff into the onto the exam. So yeah. All right. Any other questions? Well, yeah, so the exam, I'll make another Moodle announcement that putting all this stuff together written out, but yeah, the exam will be Thursday, 9:30 to 10:45. Then there will be 10 more minutes beyond that to be used for taking pictures of your stuff and uploading it. So, so you can use that time, and then essentially the process will be the same as the quiz in terms of accessing it starting at 9:30 and having it available, and then being able to work the problems and then upload in the same way. So, yeah. All right. Let's see. I'll have like a little some time too between now and then. So if you do have any other questions, feel free to email me, or we could set up a time where we could chat in Zoom. So. Great. So if there's no other questions, then just call it good. I will find a way. I'll figure out where this recording is saved, and I will upload that. Oh, also I think Kieran, you're on here. I think we had a meeting later, but I have something else I need to do. There's a thesis defense I need to attend, so sorry.
I don't think he's on here, is he?
Maybe he wasn't. I thought I saw him earlier.
He was for a second. Maybe he left.
Okay. All right. Well, I'll email him. So. All right. I'll see you all later. Probably I'll do another one of these Q&As maybe in a week or two, around when the next homework is due. So. And then of course, feel free to send me a message anytime if you want to arrange another time to meet. So. All right. See you all. Bye.